So today's the last day of the decade, and I wanted to do a fun thing. So this video is coming out at 11:45 exactly. It's going to last exactly 15 minutes, assuming I time it right. It's going to be completely live, and it's just going to be a fun math lecture that's going to bring you into the new year. I've messed up many times before, so I don't even know if I have paper left. I probably should have pulled this out before I started filming. Okay, I have enough paper. I'm going to be talking about some really fun math concepts. Let's begin. Yay! First thing, Euler's totient function. You probably haven't heard of Euler's totient function, but it looks something like this. If I'm applying Euler's totient function to a number m. Okay, what does this do? So Euler's totient function returns all the number of n such that n is less than or equal to m, and the greatest common divisor of m and n is equal to 1. Okay, that's fun and all. What does that mean? So let's do an example with m is equal to 10. First, I'll list out all the numbers that are less than or equal to 10. 3, 4, 9, 10. Now let's check which ones have a greatest common divisor that's equal to 1. So if I look here, 1 and 10, okay, clearly equal to 1, that's fine. 2 and 10, no, not okay, because 2. 3 and 10, they're co-prime, that's fine. No, 2, 5, 2. This one's okay. 2, this one's fine. And 10 and 10 clearly have a common divisor of 10, so this one's out. And I'm left with 1, 2, 3, 4 numbers. That means that the totient function of 10 gives the number 4. Okay, but who cares? Well, there's this very fun theorem that says that given A and B, or A and M are co-prime, so that means that the greatest common denominator is equal to 1. A to the power of totient M is in mod M is congruent to 1 in mod M. Okay, what's a mod? Well, let's say I told you the time right now was 15 o'clock. You would say, okay, no one uses military time, get on my level, it's clearly 3 o'clock. So I would say that 3 is congruent to 15 in mod 12, because we tell time on a 12-hour scale. Unless you use military time, you're discussing pig. So I'd say that 3 and 15 are pretty much the same thing, because 15 is just 3 hours past 12. And I can also say that this is congruent to 27, because 27 is 3 hours past 12. Past 12. Okay, cool. Another thing I can say is that, okay, let's just say I generalize it to mod base m. Any number is congruent to a plus km in mod m if k is an integer. So let's say that a was 1 and I was working in mod 10. So I can just keep adding 10. I get 11, I get 21. All of these are the same. If I keep subtracting 10, they're also the same. And these things are all congruent to each other. So if I were to look at this, Euler's totient theorem, I see that if I add m to 1 enough times, I get a to the power of totient m. Alright, why is this important? Well, we can actually use this to prove a fun thing called Fermat's little theorem, which says that a to the power of p minus 1 in mod p is congruent to 1 mod p, given that p is prime and a and p are co-prime. So that means that a and p, the greatest common factor they share is equal to 1. Alright, so first let's try taking the totient of any prime number. Well, if we list out all the numbers, let's say 7, less than 7, 1, 2, 3, 4, 5, 6, 7, right? Actually, let's do 19. It's the end of 2019, right? It's going to be a fun big number. Dot, dot, dot. Wait, 18, 19. There we go. So, I can't write. So, if we look at the factors of 19, that's 1 and 19, because 19 is prime. Well, all these numbers are less than 19, so they can't be divisible by 19, but all these numbers can be divisible by 1. So that means all 18 of these numbers have a greatest common factor with 19 of 1. That means that there are at least, the totient of 19 is at least equal to 18. But 19 is not divisible by is divisible by itself, so that means the greatest common factor is 19, not 1. So we get that the totient of 19 is actually equal to 18. In fact, you can do this with any prime, and it's always going to get p minus 1, because all the numbers less than it are going to be divisible by any of its factors other than 1, because the other factor it has is itself, and the prime itself is divisible by itself. Okay, now let's plug this into Euler's Totient theorem. So I get a to the power of this thing is in mod p, a to the power of totient p in mod p is congruent to 1 in mod p, assuming that a and p are co-prime, right? Well, since p is a prime, if we substitute, we can substitute p minus 1 and for the totient. So we get a to the power of p minus 1 in mod p is congruent to 1 in mod p. Wow, that's pretty interesting. Isn't that? Fermat's little theorem, boom, we proved it. We're so cool. Let's go. New Year's resolution completed. Okay. I'm really tired. Okay. So now we've done some weird math stuff. Let's go to some fun math stuff, like a cool math party trick that you can show to your friends. Wow, so fun. Alright, so something interesting to know is that any number to its fifth power is going to have the same last digit as the number itself. So like if I take 19 to the power of 5, which is equal to, I know this off the top of my head. I clearly know this off the top of my head. 4, 7, 6, 0, 9, 9. Right, they share the same last digit. That's pretty cool. And in fact, this works for every single number, and we can do a proof of it right here. So I can write any number, like 1, 2, 3, 4, 5, as a times 10 plus b, where b is a single digit and a is some number. Right? If I were to write 1, 2, 3, 4, 5 in this form, I would say that a is equal to 1, 2, 3, 4, and b is equal to 5. You can see how this works, right? If I multiply 1, 2, 3, 4 by 10, I get 1, 2, 3, 4, 0, and I just add the last digit to it. That means that I can write any number, x to the power 5, as a times 10 plus b to the power of 5. Okay, that's pretty fun and all, but where's the proof? Well, if I use a binomial expansion, I get this is equal to b to the 5th plus b to the 4th plus dot dot dot. Anyways, all the digits after this are going to have a factor a times 10. Well, since all these digits have a factor of 10, that means they're not going to affect the last digit. Like, if I had 13 times 10, I get 130. That doesn't affect the last digit if I add it to anything, because I'm just going to add 0 to the last digit, so we can ignore everything except for this b to the 5th. That's the single digit to the 5th power. That means if we check that all the digits to the 5th power are equal to end in itself, then we've proven it. So, all right, let's do it. 0 to the power of 5. That's 0. Wow, this works. 1 to the power of 5. Oh, 1. Such invigorating math. 2 to the power of 5 is 32. Wow, that ends in 2. Awesome. 3 to the power of 5 is 243. 4 to the power of 5 is 1024, I think. 5 to the power of 5 is equal to 3125, I hope. 6 to the power of 5 is equal to 777. Wait, actually, I don't know about this one. Frick. Oh, it is. Okay, cool. 7 to the power of 5 is equal to... Oh, heck. Give me a sec. I should know this. Alright, and then 8 to the power of 5 is equal... Wait, I can actually figure this out, I think. 2 to the 15. 6553, 65 by 2. Yeah, that's stupid. Okay, 3, 2, 7, 6, 8, 9 to the power of 5 is equal to 5, 4, 0, 4, 9 maybe? God! Why? Oh, 5, 9, 0, 4, 9. Close enough. Wow, would you look at this? All of them end in the same digit. Perfect, we've proven it. That's awesome. But there's also a proof that you can do with Euler's Totient function, which is super cool. The problem is it takes a really long time. So I'm just going to do the first step and I'll leave the rest as an exercise to the reader. Alright, so let's say that we have a number, a, and we took it to the 5th power. If its last digit is something like 4, the last digit of this number itself we want to prove is also going to be 4. That means if we subtract these two, the last digit is going to be 0. So a to the power 5 minus a ends in 0. What we want to do is we want to prove that it ends in 0. So in other words, it's divisible by 10. So we can write a to the power 5 minus a mod 10 is congruent to 0. This is what we want to prove. mod 10. How does this work? What does this mean? Well, if you remember, 0, for something to be congruent, you can keep adding whatever the mod base is, and you'll get this number. That means I can keep adding 10 to 0, and I'll get a to the 5th minus a. In other words, that means a to the 5th minus a must be divisible by 10, because I can add an integer number of them, number of 10s, in order to get a to the 5th minus a. So, in order to truly do this proof, there are 4 cases you have to consider. I'll do 2 fun cases that I really like. First case, so the 4 cases are a can be divided by 10. The second case is 5 can divide a, 2 can divide a, first case, 10 can divide a. Second case, 5 can divide a, but 2 cannot divide a. Third case, 2 can divide a, but 5 cannot divide a. The last case, 2 cannot divide a, and 5 cannot divide a. Basically, the last case is that a and 10 don't share any common factors. I'll start off with that one because it's super fun, and it uses Euler's Totient function. So let's say I have a to the 5th, blah, blah, this thing, right? Well, I can rewrite this thing as a to the 5th mod 10 minus a mod 10. This is a congruency. It's just a rule of modular arithmetic that you can work with. You can also factor things out in modular arithmetic. But the thing is, a and the base have to be co-prime in order for us to do this. So I'm proving the last case. So I'm saying that a cannot be a and 10 are co-prime. That means I can write this as a mod 10 multiplied by a to the 4th mod 10 minus a mod 10. These 2 items are congruent. Well, if we remember, the totient function of 10 is equal to 4. So by Euler's totient theorem, this thing should evaluate to 1. So we end up getting a mod 10. So a to the power 4 mod 10 evaluates to 1. So in the end, we get a mod 10 times 1, which is just a mod 10, minus a mod 10. But wait, if I subtract these 2, I get 0 mod 10. Yay! Because a minus a is 0. Wow, that's the proof. These things are congruent. Awesome. Now, the second most fun one I want to go over is the one where... Oh, I have to... Cool. The second most fun one is where a is divisible by 5, but not divisible by 2. So I want to prove that a to the power 5 minus a is divisible by 10, right? Well, I know a is divisible by, or 5 divides a, and I can factor this into a times a to the 4th minus 1. So clearly a to the 5th minus a is divisible by 5 as well. Now I want to prove that this part is divisible by 2. Well, I can factor a to the 4th minus 1 into a squared minus 1 times a squared plus 1, and I can factor a squared minus 1 into a plus 1 times a minus 1 times a squared plus 1. I'm going to rearrange so I get a minus 1 times a plus 1 times a squared plus 1. All right. Now, if you look at integers, right, any consecutive integers, any 2 consecutive integers, one of those is going to be even, right? Because every other number is divisible by 2. Well, look here. A minus 1, a, and a plus 1, that's 3 consecutive integers. So one of these has to be divisible by 2. That means there's a factor of 2 somewhere here. So that means a to the power 5th minus a itself has to be divisible by 2 as well. Boom! That means a to the power 5th minus a is divisible by 5 times 2, which is divisible by 10. And we've proven it. That's pretty cool. All right. Yay, that was pretty fun. The other 2 cases require... a bit of meddling. You can use Euler's Totient theorem, but you also have to make sure that the things, when you are factoring out numbers, that these numbers are in fact co-prime. Otherwise, it doesn't work out that well. Okay, I have a minute left. Do I have any other topic to cover? No, I guess. Pico, will I? Oh my. Yay, there's no other topic to cover. So I think I'll just look at the camera with this dog for 30 more seconds. Happy New Year, everybody. It's coming up in like 30 seconds if you live within a time zone that uses Chicago time. Wow, Euler's Totient function is pretty neat, huh? Check out my Pikachu. Okay, 40 seconds, 12, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, oh my gosh, the New Year, 5. Do I know what's going to happen? No, I don't have 20/20 vision. Wow, I got to put in. Okay, perfect, bye.